Hello again, this is Claudio from expertfa.com. Today we are going to discuss in a free manner about the simulations, the structure simulations, which load the bodies, thus exceeding the yield stress. And they undergo what we call plastic deformation, plastic stress, plastic strain. So, short remind about my website, expertfa.com. Go there and yes, hopefully you'll find something useful for you. I forgot to share my screen while showing the website. Let me share the screen. Okay, so this is the website. Go there, lots of useful things. Also, I offer, if you support contact, you have the email address, office@expertfa.com. Feel free to reach out and I'll help you as much as I can. So regarding plastic deformation, let me firstly open ANSYS workbench, then discuss a little, just touch a little the domain about regarding the stress strain curve. In principle, we are not going in detail, for example, for aluminum, for steel, for copper. In principle, this is how the curve looks like when we perform an extension. Yes, we pull out the standard probe. Let's see how it's called. Extension, maybe probe. Extension probe. No, it's not this. At this moment, I don't know how it's called in English. Okay, so this region we know it's the elastic region, and it's perfectly linear. Yes. At this moment, at this point, the yield stress, yield strain, let's say, occur. After this, the plastic domain, let's say, occurs. Before the yield strength, what deformation is applied, what load is applied is, let's say, reversible. So the deformation comes back to the initial state, let's say. After this point, hardening occurs, then necking, which will impose remanent deformation, a permanent deformation. In the end, if the force, the stress is too much, then fracture will occur. This is what we are going to discuss, this region about or above in strength. Let me go a little into ANSYS workbench, and yes, let's discuss a little. We're in the beginning, so we are going to work again with static structure. Let's design something. Let's model something close to what we shown in the trailer for this live streaming. Let's see if there is any question. Nothing. Perfect. We're waiting for space claim to open. So look here, more words. Stress, strain, elastic behavior, plastic behavior, fracture point. The proportional limit is kind of close to the yield limit, let's say. There is much theory and philosophy. I'll not go in detail because it's heavily discussed in the faculty. So where were we? Here. Let's do something like a V shape or something to form. All right. Go to plane view and maybe you know what? let's make it like a symmetry axis. And then we're going to offset something. One, maybe 25. Oh, too much, maybe 50. All right, you'll understand in a few seconds what I would like to do. In space claim, the so-called hidden, the interrupted line is what it's called construction line. So if we uncheck here construction, we're going to have a full line, yes? Construction line, this hidden interrupted line, is not extrudable, is not, let's say, part of the final sketch. It's just helping geometry. So we will uncheck it here, because I would like to have a V shape, all right? So let's be a little more, something like this. How much should we do? 3.5. Then we're going to have something like this, like a V shape. All right. We're going to mirror this. Mirror command. We select the mirror plane, which in our case is a mirror axis. And we select what we want to mirror, this and this. All right, we're kind of set. In Sketch, we have the trim command. And we're done. This is what we need in principle. We can delete this, but let's leave it like this. We're going to make some filets for radiuses, but I prefer to make them in the 3D, okay? Let's extrude a little. We are proving a point. This is for tutorial purposes. Let's not make it too thick. 5 millimeter, it's more than enough. So I was talking about some filets. These two, yeah, were in the pull command, and the pull command has many options. The first option is the filet, the rounding option. Yes, we drag and drop, or we can write a value. Let's write 1 as a value. All right, and here inside this edge, we're going to, how much? 1 again. Let's make it 0.7. All right, for faster solving, let's decrease a little the thickness towards, why not 2? And because this is unused material, let's also decrease here. 4.5, also here. .5 and 1.5 here. We would like a very fast solving, let's say. All right. So let's make the blank, the workpiece that we are going to bend plastically, okay? So I click on a face, design, sketch, plane view. Let's make the blank. The easiest way is to project an existing edge, let's say. This edge, I kind of want to offset it. Let's see if it works offsetting this edge. Yeah, it works. We're going to zoom in. Remember, control middle mouse. We're going to zoom in order to leave a very small gap. I don't want it to be perfectly collinear, but a very small gap. Maybe 16.05. Yes, perfect. There is a small gap. Let's also offset this one. And how much should we offset? Maybe I'm looking sincerely at the radius here, this radius. This is why I would like to kind of not exceed a common sense. Let's make it 0.3. And we're closing this rectangle, let's say, with escape. We exit the command. We're closing here. All right. In principle, we should have a rectangle. Look here and here. Alrighty, let's pull it until there is this command up to until it meets this face, let's say, okay? And we have two different bodies. You can see them here. All right, my preference is to make the workpiece a little longer, 1.5. 1.5. And yes, regarding the geometry, this should be all. You need to take this into account. Yes, the thickness is 0.3, and it will somehow let's offset in order for you to understand the principle here. Look. We're going to kind of simulate what will happen after the FEA is solving. Look here. Let's offset this this curve, if it's possible. Is it possible? No, we need to firstly project it. I will project these curves. Then we're going to offset them. Look here, yes? So when I was searching for the radius, I took this into account. And I left it as thickness, I left it 0.3, if you remember at the beginning. The thickness is 0.3. 0.3 ensures that here we have a radius. If I was to make a higher thickness, 0.7, then it would have mandatory, it would have been a pointing or a very sharp edge here or point here. Yes, this is why I chose 0.3 as a thickness in order to have a radius here. Yes. I will not undo. I will get out in the 3D, and here regarding the curves, I will delete them, and we have only the 3D model. All right, so let's make this even thinner because it's not so important. Let's also save the project. All right. File, save as stream 3, January 4. Plus a deformation, and I'll put a V shape. All right, we can close space claim, double click modal, and we're going to access the mechanical window. Any question? No, perfect. So plasticity occurs in, let's say, elastic materials, in materials which support or allow an elasto-plastic regime. Okay, we're not talking about hyperelastic, about rubbers or silicons, about fluids. We're talking about metals, plastic materials, maybe composites, wooden fibers, where fracture occurs, let's say. So F7 to zoom extent everything, yes. I am running, I will, let's say, firstly rename. This will be the die, and this will be the piece. Firstly, we will run with the default structure steel. The default structure steel has only defined the elastic regime, let's say, until the yield stress. You can see it here. Engineering data, double click, and the default structure steel has elasticity defined. Isotropic elasticity. Nothing about plasticity. Yes, we have a Young's modulus and the Poisson ratio, and that's all. This does not say anything about what happens above the yield limit, about the plastic domain. Okay, we have something, let's say, regarding fatigue here in strain life and then SM curve. Okay, so let's run it elastically. Yes, we can rename it elastic. Let's see the contacts that we have. Only one. Right click, rename based on definition. Because clearly the piece will touch these faces, I would like to extend this red region, let's say, yeah? The red region is called the contact side of the contact. Even though it's a mouthful, this should be called source, but in ANSYS it's called contact. I said it before. Let's extend it a little, okay? The easiest way is to click here and then go to selection, adjacent, or limits, adjacent. Look here, again and again. Apply. So we have the underside of the blank and the entire V shape here, okay? Now I found out that we need something to push. We can push with the force, no problem, but it would be nicer with the punch, okay? So this is kind of mandatory. Before doing this, let's apply here a frictional coefficient, 0.1, let's say, and we're leaving it like this. Again, right-click, edit geometry in space clean. So in principle, we're doing what is called cold forming. We're plastically deforming at room temperature. So the offset that I mentioned before is useful. This means we're going to click this face, design sketch mode, let's apply it at let's project firstly these faces. we don't need the radius. You'll see in a few seconds. Now I'm going to offset. Offset how much? I will need to take into account this thickness, yes? And the thickness, let's say, can I measure here? Let's see. 0.3, yes? Let's offset. So we're going to offset more than 0.3, okay? In order to take into account the thickness of the blank. So let's say 0.35. In principle, we don't need this edge. It's not needed, so we can escape. We can click them and delete them. Now, let's kind of build the punch, all right? Not too much. 2 millimeters should be enough. We don't care how long it goes because we're going to mirror this. Mirror about this axis, we're going to mirror this line. Now where we come with the trim command. Yes, that is all. Again, let's delete them because they didn't disappear. Do they disappear? Yes, finally they disappear. Come on. Yes. Now this should be the punch, let's say, okay? Maybe this, now is the time to move the punch a little higher. Let's select it. We have the move command until it meets the blend, yes? Let's make it as close as possible in order to have like a closed contact. 11.19, is it possible? Yes. For my likeness, I would like around here. Yes, let's do this. Pull up to here. Let's round here generously. I'm clicking these edges. Fillet is pressed. How much? Generously means 1. So much generosity. All right. Normally, for explanation purposes, what we can do now is cut even more, but it will be an overkill and it will maybe confuse people. So let's leave these parts as they are right now. Right click, update geometry from source. Let's see if we have any question. Oh yes, interesting method. I don't know if you can see. Let's see. Yeah, interesting method. Thank you. And this is only until now. We're going for the default thing. We're going for the elastic regime, and in the second phase, we're applying the plastic domain to the plastic definition. In the next hour or something piece. This should be called punch. Let's put the default structure still. Right-click, rename based on definition. We have two more contacts. This was defined, die to piece 0.1. This is die to piece. It's already defined. This can be deleted. We have the punch to die, yes? Piece to punch. You understand that in a very short time, this, okay, they will touch. So this means also these two faces need to be added to the so-called target side, okay? Let's go for target and click adjacent here. And we have now also these parts, these faces. Apply. Should we also include these rounds? Yes, why not? So click here, adjacent again, apply. All right, of course not bonded. Frictional 0.1. Remember about the modifying these contacts, because I've seen lots of people, they leave it as default, they leave it bonded, no separation, which is completely wrong, of course, and they get wrong results and wrong behavior. Let's save. Right-click, generate mesh. Ooh. We can all admit it that it's pretty coarse. So yeah, let's refine it a little. We are mostly interested in the blank. The punch and the die, we're not very interested about what happens in now. I like very much going for the tetrahedron mesh. So let's do it. Feel free to experiment with hexahedron and whatever you like. Let's give a sizing to the punch. Click the punch, to the blank, I meant. Sizing, and how much should it be? You know what, let's try with 0.7 and see what happens. Please remember that in principle, we should have at least 2 elements per thickness. At least 2 elements per thickness, in principle, to have reliable stress and strain results. But here, for fastness of solving, we are satisfied. Let's say for tutorial purposes, we can go with only 1 element per thickness. Right-click, rename based on definition. Let's now go for the sizing of these two parts. How much should it be? Maybe 1? Or no, even 1.4, 1.5. Why? Because I would like to create another sizing with changing the selection filter to face, Control F, or you can go here, cursor mode, face. Yes, I would like for these faces, let's hide the blank, hide. I would like these faces to have such a sizing. I will refine this mesh, so this is why I'm selecting only these large faces. Apply, and maybe, I don't know, 1. Let's see, let's generate mesh and we will understand a little more in a few seconds. Yes, right-click, show bodies. It's still a little too coarse. So these are not 2 elements per thickness, it's only 1 element per thickness, okay? Right-click, cursor mode, element, and you can see this is a tetrahedron. It's 1 tetrahedron here, 1 tetrahedron. We don't have, if this edge were to be split in 2, then we would have had 2 elements per thickness. So right-click rename based on definition, right-click rename based on definition. Let's make this 0.5. This was too coarse for my liking. Instead of 1, let's make it 0.7 maybe. Right-click, generate mesh. So we're approaching what we need. Let's see a little these. You see, they are not very, they do not define, approximate the curved surface very well, these tetrahedron elements here. This is why right now we're clicking sizing, then selecting these filets, and we are applying here maybe 0.3. Right-click rename based on definition, right-click generate mesh. So it's fine here. We have almost a very nice curve. Also here it's kind of acceptable. And in order to have a proper contact between these faces and the blank, let's refine just a little, 0.6, yes. And also the piece or the blank, show all bodies, let's make it 0.4. Yeah, this is nice. Let's look at the stats, okay? Under 20,000 nodes. This is perfect. All right. The first thing we are going to do, let's measure from the airplane. Should we measure from the airplane, or how should we measure? Let's measure in space claim. I would like an exact dimension. Remember that when we added the geometry, usually by default ANSYS adds new bonded contacts and new fixed joints. Just remember about this in order to reassess and maybe remove the additional unwanted contacts and the joints. So I said that I will measure the distance between this edge and this edge. All right, measure. We need to take into account that it does not measure the exact edge, only until the axis, until it meets the axis. This means that we need to also add this radius, yes? So the radius here is 0.7, and we're going to add 0.7 with 10.5. This means 11.2, all right? 11.2. Why I'm talking about this? Because I would like to assess the travel of the punch. The punch will come down, and I need to assess how much should I press the punch, all right? So let's maybe also measure between these two surfaces, let's say, and we have 11.2 as I kind of said. So we're going to apply 11.2, and let's see then what will happen. Let's do it in 3 steps if it's possible. I don't know if it will be possible in 3 steps. Let's see. Large deflection on, yes, where we have like a mechanism here. It's not, let's say, strength of materials. Large deflection on. All right, we're going to leave everything by default. The contacts that you have seen before, yeah, they are program controlled. And also for analysis settings, the time steps will be program controlled. I'm looking for additional contacts that maybe it put, but no, because it didn't modify geometry, only made some measurements, then there is no additional contact. All right, let's make it very, very simple regarding the boundary conditions. Very simple would mean something like this. This is a fixed face. These two faces should be restricted to move in plane. We apply a frictionless restraint, and it will move only in this plane, in the z-axis plane. Yes, these two faces. We need to add as much as restraints as we can in order to remove many of the degrees of freedom. Yes. And let's press. We're going to press this punch. Yeah, let's select as many faces as we can. We're going to leave those. Displacement. The displacement should be, of course, about x-axis, and we select here tabular. In order to remove some degrees of freedom, we are going to select 0 for the y-axis, yes? Let's make it 0. Do we need the z displacement? No, we don't need. Let's make it 0. This will help very much the solver. It will be much quicker. Let's see if we have any questions. We have any questions? Hello, can you please tell me how to do hyperelastic simulation of a body? The geometry is to be done between, oh my god. The hyper is wrapped around the hyper. Yeah, it's a little much. It's not the purpose of this FA, but I will answer. Insert hyperelastic material from engineering data. Apply the correct parameters. Yes, I'm talking about mooney, rivlin, Yeoch, Ogden, etc. It's hyperelasticity is it's not for beginners. So yeah, familiarize yourself, and in the beginning start with the materials that you have at your disposal in ANSYS. I can, you maybe have seen it, engineering data sources. You have here hyperelastic materials. Yes, you have already, I don't know how many, maybe five samples here. What you need, according to your material, you'll need to modify some stress strain values. Yes. New Hookian, yes. Good luck. It's it's not for beginners, so start from somewhere, okay? Where were we? Here. I told you that we are going to displace it downwards in the positive direction of the x-axis. And the kind of the maximum value should be around 11.2. Let's divide 11.2 by 3. It will be 3.8, let's say, yes? 3.8. 7.6, and here I will impose 11.2, even though it should be a little higher than 11.2. Yeah, it's not perfectly. It's not a perfect line, okay? Because here should have been 11.4, I think. So just for fun, because of course I predict there will be problems, we will run it with elastic default. Let's apply some basic solution items. Toolbox contact tool. This is very nice usually. Friction, stress, pressure, penetration and gap. These are very nice to have. All right, save. Look what occurs. Look what happens when we leave the material elastic. Yes, these are curves for fatigue. We're not interested. Here we're interested in the elasticity. So this radius should be the sum between the thickness, this thickness, and this radius, yes? It's a common sense knowledge known by forming experts, by the ones that work with deep drawing. Let's solve again. What if you select a brittle material for the blank, say glass? Will you be able to capture a brittle failure in this simulation? Not in this simulation, because when you have static and transient structural, you do not have failure. You do not have mesh erosion. You do not have breaking. The only simulation where you have breakage, failure, fracture is explicit dynamics, because explicit dynamics allows mesh erosion. Let me give you a small example. Look here. I will show you a simulation, some simulations of mine made with glass. Look here. For example, yes? Made with explicit dynamics. Explicit dynamics allows such fractures and mesh erosion, not in static, not in transient. Another, yes, this is interesting. I don't like yes page too much, but this is what you need. Look here. Yes, this is fracture. Also made in explicit dynamics, not in static and transient. So yes, in future streams, I will also make fracturing in explicit dynamics. Just have some patience, a few days, okay? And I will also perform live such simulations with fracture in explicit dynamics, not in static, not in transient. I hope this answers your question. Why did you apply the displacement in 3 subsets instead of 1 subset? So let me answer your first question. Fracture in explicit dynamics only. And why did you apply displacement? To refine or to gradually apply the load. This is, you don't come in one step with the full load, you make divisions, you gradually apply the boundary conditions. So yeah, this is a small trick, let's say. I'm not getting converging, trying to simulate Kibon actuators. The problem is with convergence. What could be the possible types of parameters I should consider? Firstly, I will need to see what Kibon actuators are. Let me check them after I hit solve here. Yes. Thank you for the questions and for being present here. I'll be back once I hit solve, because usually it gets pretty boring while solving. So we should have here some log, some writing, and it's not here. Let's hit solve. We have a warning: contact status has experienced an abrupt change. Of course, why not? So I hear the fans from the computer. When we give many cores, the fans start working so much. Look what happens. So it starts to do something, then it stops. Yes? Let's animate a little. Yes? This is 0. This is, you will see from some people, you will see such simulations, which is 0. It's nothing. Yes? What does the solver say? The solver engine was unable for the nonlinear problem as constraint. Please see the troubleshooting blah blah and unconvergent solution. Solver pivot warnings or errors have been encountered during the solution. This is usually a result of an ill-conditioned matrix, possibly due to unreasonable material properties, another constraint model, or contact-related issues. Let me tell you something. It's this one, the unreasonable material properties, because we kind of bend it too much, and yeah, it's we need to define also the plastic portion. But because we like to push things more and more, let's refine a little the mesh. I'm talking about not this mesh, but this mesh, for example, 1.2. This mesh, let's make it 0.5, and the mesh in the radius is 0.2. Right click instead of 19. Now we have 26,000 nodes, okay? Let's hit solve again. And see what errors we get again. Yes, to refine. Out of curiosity, what is your hardware configuration? Yes, in a few seconds, I will answer. McKibben actuators. I'm curious because I'd like to see what Bill McKibben actuators. Muscle actuator or pneumatic actuator? Let's see. So I think they're like some balloons. I think McKibben artificial muscle. Yeah. So it's something that is inflated. Like a small pump, let's say. Yeah. And your question was, let's go here. I'm not getting convergence trying to simulate McKibben actuators, of course, because you should have hyperelastic materials, and that might be the problem. You need lots of experience to work with those materials. With convergence, what could be possible? The parameters should be defined by your material supplier, either Ogden, Yeo, or Mooney, rivlin, whatever. That is the problem only in the material, and also be very generous with the ANSYS settings. Define very small time steps. Define very small time steps. This is my answer for you. And poly universal regarding the something like this. My configuration. It's a Threadripper 64 physical cores, 128 gigabytes RAM. It's not too much, but also not zero. And I advise always to have NVMe SSD. Yes, NVMe with very fast speed, at least 4, 5, 7 gigabytes per second. And the video card is pretty recent, 5080. Yeah, it's for at home. It works. It's good. It's nice. Wow. Yes. It also cost me. It cost me a little. Yeah. So where were we? Here. Clear generated data. Yes. Solve. Right click, yes, solve. What I recommend for faster speeding, for quick solving, HDD, classic HDD, out of the question. SATA SSD, out of the question. Only NVMe SSD, okay? So as small reminder, I'm writing NVMe SSD here. These types, okay? Now I think we are on the generation maybe 5. Yeah, generation 5. Look here. This means maybe 12 gigabytes per second. Let's see if it's. Yeah, 12 gigabytes per second. Yes, ANSYS is writing on these drives, on the hard drives. So let's say on the SSD is writing information, is writing the solution. This needs to be very fast. I would say this needs to be very fast. Also, multiple cores, preferably higher frequency, and some RAM. Yeah, the RAM is not very important according to me. What I know, if I remember correctly, the intrinsic speed of RAM is 24 gigabytes. So with the NVMe, with the hard drives, let's say, we're approaching the RAM speed, which is extremely nice. We're living nice days. So, shocking or not, the FE works. even though I would not have expected to work. No, it does not work because there is no log here. So if you have a laptop with 4 cores and I don't know, 16 gigabytes of RAM, and don't expect too much, okay, from the simulation. But nevertheless, if you're a student or you're working in a company, if you're a student, you should have access to the network, the computing network of your faculty. And if you are in a company, of course, the company should possess a nice computing system if they want results. If they not, yeah. So we can see that it's not happening. Okay. Something is not right. Okay. Why? Because we are only going towards on the elastic regime, as I showed before on the stress-strain curve. We are here, but our load, our displacement is too much. In order, and plastic deformation should occur. If we are going only on the elastic regime, we're kind of forced to have like a stiff material. If we have like a stiff body, then the FEA cannot converge anymore, cannot solve anymore. When defining plasticity, a certain softness occurs. Yes. Then we can move on with the punch. At this moment, let's close this FEA because I would like to go towards plasticity. Afterwards, this is the motto, the topic of this simulation, harmonic deformation and plasticity. All right. So let's duplicate here. Any new question? Let's see. Yes. Well, thanks. Yeah. Thank you. Thank you too. I'm moving this because I know that this is my window, my overlay, my webcam overlay. This is why I'm moving the chat for you to see, for everyone to see what messages I receive. All right, so here we're double clicking data, going to engineering data sources, and we're contemplating not general materials, which is default. We're contemplating and focusing on general nonlinear materials. All right. Let me look a few seconds at my smartphone. I have an SMS. 1 second. So I answered it. We began with steel. All right. So where is steel here? Here. Structural steel, nonlinear. Nonlinear means we exceed the elastic regime, we exceed the yield point, the proportionality limit. So yes, let's click here, add to engineering data, the yellow sign, the plus sign, and let's make like a small comparison. All right. We have structural steel and structural steel nonlinear. So besides isotropic elasticity, we have bilinear isotropic hardening. In translation, plasticity, all right? Because we have the elastic regime. This is the elastic regime domain defined here in isotropic elasticity. And we have also the plastic domain, okay? Which is defined with the help of tangent modulus, all right? So let me make a small screenshot in order for you to have a broader view on this topic. I will make a small screenshot, I said, come on. So you remember that this, let's make like a triangle here, okay? So let's call this sigma elastic, okay? And let's call this sigma plastic, even though it's breaking. I will call it breaking. All right, so we have 0 here, and what I wanted to show you is something like this. Let's say this is horizontal, let's say, okay? If we have this, the alpha, this angle, when we make tangent alpha, it's the opposite side, yes? This is the opposite side. Yeah, over this stress. But, sorry, opposite side over the near side, because this is so-called elastic strain. Yeah, this tangent alpha, it's called Young modulus. Young modulus, and it's kind of it's a modulus for the elastic domain. This is the modulus for the elastic domain, for this domain. There is also a modulus for the plastic domain, and this angle towards the horizontal, yeah, between the inclined portion and the horizontal, this angle is the same. It's this portion over this portion, let's say, yes? So we have tangent beta, which is called tangent modulus, is the last sigma, let's say, sigma breaking sigma. I will write it breaking over this epsilon, over the strain on over the plastic strain, let's say, yes, plastic strain. It's called tangent modulus, and it's like a modulus for the plastic domain. This is what this value is, tangent modulus, yes? In comparison with the Young's modulus. Young modulus is the modulus, is the tangent alpha for this triangle, for the elastic portion. And the tangent modulus is the modulus for the plastic portion, let's say. You can see maybe broader explanations on Google, they're explained even answer. But these describe the plastic domain. All right, where were we? Here, double click. If steel is too rigid, maybe we'll change it to to aluminum, maybe, I don't know. We'll see. I think the thickness is too much. It's kind of too much. 0.3 is kind of too much. So for the piece, we're changing the structure still to nonlinear. Yes, something like this. Do we have? Yeah, we have. I don't know what is y is 1 and 2. We don't care, but we can see the material. So ignoring these parameters regarding to fatigue, we see here. Yes, also the plastic portion is defined. Let's see if it advances more than just an attempt. Okay, save and solve. Where are we here? Any more questions? No. Let's go on some YouTube simulations. We have convergence. Look here, forced convergence. The FA works. Let's see how much it will work. Where are we? Here. So I think you have seen it until now. Look here, 2 elements per thickness. Yes, this is the correct way to do it. Plasticity, any more plastic? Yes, this is something very nice. I will comment in a few seconds. This is kind of fracture, let's say. Can we change to plasticity? Yes, this is nice. This was my first tutorial, let's say. In 3 stages, it's getting a little thinner and also bent around some of the cylinders here. This is pretty complex, and yeah, it took some time to solve it. The contacts are a problem here. No, this is standing, so no, the contacts are not a problem here. I have a similar simulation. Can I find it? Of course, not when I need. We will do something like this in the next streams. Yeah, this was one of my first tutorials. Yes, we removed the punch and the deformation remains. This is remnant deformation. Hopefully today we will get something like this also in our simulation. So we have 3 steps, and we're almost in the middle. Let's see what occurs here. It advances more, yes. Then yes, I think it's clear that we are on the right path. A remark that I wanted to make in equivalent stress, yes, in principle we should not, and we cannot exceed the breaking value, yes, the ultimate tensile strength in principle. So a golden rule, if you want to have reliable stress values, you need to almost always use non-linearly defined materials, because it will allow isotropic hardening, a local hardening. And yes, with the stresses will not be like, maybe you have seen beginners which show 2000, 3000, 5000 megapascals, and that is completely unreliable and not useful, okay? Let's see, my steel could be a little too much rigid. Then we maybe we'll change it to aluminum. I will see what happens in this portion. I predict that the solver will stop. We'll have problems here in the end. All right, we were here. This is made in explicit dynamics, and yeah, it looks very nice. Yeah, also Riemann deformation here, because I also removed this this part, and the plastic deformation remains. Another application of plastic deformation, machining. Here is an example of mesh erosion, only possible in explicit dynamics, not in static or transient. This is also occurring in water. It was, the efforts paid off because it looks extremely nice. Here we have something very useful. And it's easier simulated with ANSYS coupled field, transient or static, but it should be coupled field. Due to the plastic strain, due to the plastic domain, heat is generated due to repeated deformation. You know, when you want to break a wire, you bend it repeatedly, and it breaks. Here we can see the heating that occurs due to cyclical load. Look here, we have 1, 2, 3 cycles, and stress and heat accumulates. I will show you temperatures, I hope, soon. Energy potential, tension accumulates. Come on, do we have temperature or not? Maybe not. We have watt per cubic millimeter. Ah, yes, this is the temperature, yes. and we reach around above 100 degrees Celsius due to repeated loading. We'll do something similar in future streams. Let's see plasticity from other people. I'm interested. .5 almost in the middle. Yeah, it's too rigid still. So I would propose. Otherwise, it will take a few good hours to solve this, and I need to refine this corner here. When talking about steel, I will propose to change the material to aluminum because it's much softer. Let's leave it a little more, then we will change to aluminum because otherwise it will take much more time to solve. And I would like to have decent results in this live stream, not in another day. Where are we here? Metal plasticity, ANSYS innovation course. What is this? Yes. And here we have shape memory alloys, I think. Stamped paper clip. So, yeah, listen to and watch these explanations. We're going for ANSYS for the example. For the applied FA. Tresca, more from Mrs. Yeah. Hardening of plasticity. Metal plasticity, come on. And now I think she will introduce the tangent modulus, I think. Yes. She calls it hardening modulus. We should... Plastic strain. Plastic strain, yes. Okay, yeah, why not? You should remember this in order to calculate tangent modulus. You're in ANSYS, you should call it tangent modulus, all right? So, in order not to confuse people. Very cute example with this paper clip. Because the lamella, the workpiece, is maybe too stiff, it can happen that the nodes, the mesh will penetrate, will snap into the punch, because I used a very coarse mesh here. If I will use a very fine mesh here, then it will be hard enough to withstand what the lamella exerts back. Yes, this is the secret. If you have a very coarse mesh, then it's kind of soft. If you want to make it harder, or let's say stiff, you need to apply a resizing and make it finer. Also, there is this reason, the fact that the nodes should encounter other nodes. Yes, so these nodes, let me change the cursor to node. These nodes from here or from here, from other side, should find nodes here on the punch. And if you have only one node here and one node here, you don't have nodes usually. You don't have other nodes except the mid-side nodes. But we should need, normally we should need, let's say, much refined, a more refined mesh here, in order not to snap back, for these nodes, not to jump into this mesh and stop the simulation. I think you will understand more in soon. Amazing or not, yeah, it works, and we accept nice behavior. Why not? We also need to accept when things work nicely. What do we have here? I think we have some questions here. Think. Do you use correct version of ANSYS? Who uses something like this? Nobody uses something like this. So I'm using an evaluation version. You read between the lines, okay? Cristobal Sanchez. Hola, Cristobal. How do you do? Thanks for that, Claudia. Gracias, Cristobal. Also, do you think Kubernetes will work like stand? Yes, it can be. Yes. Inner pressure, yes. Feel free to apply an inner pressure, yes. Go for it. Josh Dudley, I hope. Cristobal Sanchez, how do you do? All right, application of metal plasticity. So this is a very cute example. I mean cute, why? Because it's also very simplistic, let's say, and it's very easy to understand. By the way, regarding the stance, this is a steel, yes. Considering the longitudinal for the two ends, yes, she gives lots of useful information especially after release. Yes. 0.1. This is the plastic strain. I will show you the plastic strain soon, once we stop the FEA and have results. Yes, nice. Course summary. Well, in the end, advanced plastic conclusion. Thank you, ma'am. Very nice. How to topics in metaplasticity. Define multimedia. We know how to do it. Isotropic hardening analysis. Plasticity. Let's see. Structures with Prof. H. Mr. Hedegaard. Brock Hedegaard. Civil engineering. All right. He goes tangent modulus. Perfect. Strength. Very professional explanation. He defines it custom manually, okay? He goes for multilinear isotropic hardening, which is different from bilinear isotropic hardening. Let's say multilinear isotropic hardening is more professional, is more reliable. And yeah, bilinear isotropic hardening, it simplifies the entire curve. This portion simplifies it with a straight line, which it's an approximation, okay? But multilinear isotropic hardening, it's much desirable, correct, reliable, and you can see it. You'll see it in a few seconds. I think he's designing the specimen. Tension specimen. Tensile test specimen. Finally, yes, this is what I wasn't remembering in the beginning. It's called tensile test sample or specimen. And when we pull one of the ends of these, we get these curves. Yes, where are we? He is using, I think, a symmetry on this specimen. He uses maybe a quarter symmetry, maybe. $34,000 subscribers. Oh my God. I'm struggling with 10K now. Yeah, because he's explaining. Yeah, he takes his time. Lots of effort. He's a teacher after all now. Symmetry, yes, as I said, default symmetry. He uses a quarter symmetry. I will subscribe to Mr. Professor because his explanations are so nice. He already solved it, but what did he do? He applied displacement. Also taking into account that he has a symmetry, and the symmetry kind of fixes, let's say, restrains the specimen. So it's a displacement is enough due to the symmetry. He didn't waste time to show the solving. He is showing the results. Plastic strain, look here. There's some necking there. Oh, American units. Pounds per square inch. He's discussing what? 5,000. How much is in megapascals? 344 megapascals. Okay, 50,000. Okay. Very nice values. This is the real size. Yeah, not very fine mesh. He didn't have contact with punch as we had, so yeah, he didn't need so fine mesh, but he could have refined a little, just a little. Nevertheless, the lesson is very nice. Let's see other videos from this professor. 10 lessons. Microplane modifier. I think they are very thoroughly and nicely explained. Only for my taste is, let's say, it's not so complex. It's not. I prefer to have more complex topics. Let's say. He's a teacher and he's a professor. He explains it in detail. Do you? Yes, thanks, bro. A lot of my doubts are cleared during your videos. Well, thank you too for the appreciation. Thank you too. And remember to exercise. Then the results will appear. Yes. Now the symmetry. I think he's doing a 3-point bending, I think. One of these, maybe this side, maybe is the middle, maybe. He has beams. Ah, he has reinforced concrete. Oh, yes, look here. Oh, nice. Yes, yes. He reinforced the beam. Yes. This is why he has those cross sections here. Where are we? Ah, very nice. Almost second step. Nice values, yes? 330 megapascals, not 3000. Yes, Mr. Professor. Symmetry, contact. What contacts does he use? He leaves them bonded? Come on, please, no. No, not bonded. Come on. He leaves it bonded in order to avoid the convergence problems. He goes for the easy way. He's a real professor. Because he's avoiding the problems that occur. While in my streams, I don't know what will happen in the next 5 minutes. Yes, so this is why I'm usually doing the geometry from zero, and everything is kind of ad hoc and unforeseen. And this gives you an opportunity to understand how an FEA expert works, how is he thinking. And yes, also I traverse my times when I'm stuck and I don't know what to do and how to solve some problems. But in a few seconds, minutes, hours, I persist and I find the solutions. And yeah, and yeah, doing these live streams, you have a sneak peek inside the mind of an FA engineer. So yeah, I think it's for your own benefit. Mesh. The directional deformation should be on the z-axis. This is on the y-axis, I'm sorry. Does he use y-axis? No. He should use y-axis because this is the direction of the bending. Yeah, please change it to y. Come on, please. Yes. Yes. Adjust to visible. Finally, yes, this is correct. No more stress, whatever. Yeah, and in the last years, the ANSYS evolved much, and we can easily simulate reinforced parts. I would like to show you some of my simulations with reinforced. This was some of my first. This is pretty cute. This is nice. This is nice. Ooh, this looks nice. It's not mine, but it looks nice. This was something. It's not. This is what I want to show you. Another reinforcement, not concrete, not rebar. So much work. Yes. Where were we here? Do we have second? Do we have almost? So where were we? If he compares the concrete column reinforced with steel versus carbon fiber. This is pretty recent, I remember. Yeah, 2 months ago. Steel, rebar, and carbon fiber. There are some pretty small differences there, easy, hard to spot. This is seismic simulation for a reinforced silo with acceleration on the all-axis. Yes. Look here. It's pretty nice. The quality of the videos from ANSYS, come on, it's so awful. They should solve this thing. The video export quality. So look here. Yeah. Very nice. So another, and yeah, it's something similar, I think. Before going, any questions? Thank you to exercise more, yes. Nonlinear analysis of reinforced concrete beam with large web opening uses ANSYS workbench 2019. APDL, come on, APDL. APDL is not very user-friendly for beginners, so he has made this in, I don't know, Revit maybe, because we have Python Revit here. Is it Revit? Maybe it is Revit. Link Revit, yes, it might be. All right. Oh. Three rebars. All right. Concrete stress strain. Yeah, the maximum is around 50 megapascals. He's doing. He's defining the material model with APDL. Okay. Most concrete design codes specify maximum usable compression strength at which the nominal moment strength of the section is to be calculated. For the ACI code, this maximum usable strain value is specified as 0.003 for the Canadian concrete. With Bilinear, yes. Tangent. What? Come on, don't leave tangent modulus 0. It will be perfect plastic, no? If you leave it 0, it will crush very soon, let's say. Okay. He defines some beam profiles, but the geometry is already made in Revit. Okay. What? He has separate DWGs, separate files, drawing files, let's say, for the rebars. He is importing each one of them. Oh my God, it's a little complex. 3-point bending, yes, I think, yes. Defining the cross-section for each rebar, yes. Yeah, it's a lot of work, and but the results will be very satisfying, yes. This is something professional looking, yes. Now we have the dude, you lost us, dude, here, because it's not beginner friendly. So let's see the result. It looks nice, yes, but I think you can do it without APDL, with lots of work, of course. Ah, yeah, he made a comparison, yes. Yeah, really nice, Mr. Tanapon Baumko. Something from Southeast Asia, I don't know, maybe Indonesia, Malaysia, Thailand. Yeah, this is nice. What is the software? Ah, Yatabs, yes, I know this, yes. I'd like to see some values here. Acceleration maybe in G. North, south, east, west. Vx. Shouldn't this be speed? Oh my god. Myanmar earthquake. This is Mercalli scale, maybe 7.7, 2025. Yeah, it looks very nice. Where are we? 2.2. Well, now I think the problems will start to appear here in this region. I think maybe. But yes, we're satisfied with what we have. This looks like ANSYS. Yeah, very nice. Lots of nice work here from Mr. Tanapon. Yeah, respect. And this here I was crushing a beam. Let's say too much. This is why I said catastrophic load here. And here I want to show you a reinforcement with polyethylene. This is a comparison between polyethylene and steel. This is the steel wire reinforcement, and this is the polyethylene. Steel This is polyethylene reinforcement, and this is steel reinforcement. Maybe I should have mentioned this. I don't know who understands it right from the beginning. So in recent ANSYS versions, we can reinforce almost anything and everything. Thank you. Kindly ask, what project are you working right now? What project? This I'm showing how to simulate plastic deformation. Or if you're asking about in my work, I work in automotive, so yeah, I cannot say what I'm working on. So yeah, singing fingers. I tried to perform a model analysis of two different materials. Ductile. How do you spell it? Ductile? Ductile plus elastic, assembled together in a structure. I want to see the vibration effects. But I failed. You didn't fail. The FE failed. Okay, you didn't fail. Come on. What could be my mistakes here? Small questions. Ductile means above yield going to plastic. I mean in your expression. Ductile, you're going above plastic in your expression, okay? Because where I want to lead you somewhere. In modal, we don't use nonlinearities. We don't use usually nonlinear contacts, frictionless frictional. We don't use nonlinear materials. This is the problem. If you define the materials with nonlinearities, with plastic domain, then I don't see the help, the purpose, the usefulness. Yeah. I will remake the FEA, but also I will draw back the punch in order to see the remanent, the plastic deformation, because in this simulation I only applied it, I only bend it. I didn't retire the punch, let's say. Where are we here? So this is a tension test using SPH, smooth particle hydrodynamics, small spheres. But I think this is glass. Yeah, I think this is glass. Glass probe, yes. .21. It goes a little too slow for my taste. All right. Because I would like to have the backwards movement, the retirement of the punch, I will interrupt it here and change the material to aluminum and retire the punch. I will also write here steel, nonlinear. This is steel simple, elastic, save. Oh, yes, what I wanted to see some deformation. Yes, elastic strain. Yeah, so it exceeded the elastic domain. And here we are going to the plastic domain. I hope. Let's go for solution, strain. Do we have a total strain? Equivalent total, okay. And then we have equivalent plastic. So the total strain is 0.04. Yes? So you can see the difference. The total strain is 0.047. 0.047. The portion of the elastic, the plastic strain 0.045, and the elastic strain is 0.001. When you add up 0.0016 with the elastic portion with 0.0045, you have the total strain 0.047. Yes. If you do FEA and you have 0, yeah, the easiest way to check if you have plasticity is to insert such a solution item, plastic strain. Yes. If you have a value above 0, then you have plasticity and you have remanent deformation. Yes. Right now, you cannot easily see the remanent deformation, the plastic deformation, because we didn't retire the punch. Yes, there should be like a spring back, and it should retain the blank, the workpiece should retain a V shape. All right, pretty cute. Let's see status, stress, pressure. Yeah, it looks nice. Remember to always change, draw here in order to have even nicer values. Yeah, here, something like this. Yeah, just play, have fun, because the domain is, if is not easy, it's complex. But remember to have fun, to play, and you'll experience. And by playing and having fun, you'll begin to like it. And then it will not be a burden for you. Yes, if you are just playing, you are discovering with curiosity in your mind, and yeah, it will be very nice. And then you'll, as I do it, I at work, I'm usually having fun, and I don't believe they are paying me to do FEA, to perform simulations, because it's what I like. So here on engineering data sources, let's go and insert an aluminum alloy nonlinear, which should be much faster to solve. And also let's retire the punch, as I said a while ago, in order to see the deformed workpiece, the plastically deformed workpiece. Here I will change the material of the workpiece to be aluminum when ANSYS will let me. Come on, let me. Piece aluminum alloy nonlinear. Let's look again at the connection. Look here, huh? It gave me 2 additional bonded contacts that I don't need. And look, let's look on the meshing. Is it correct? Yes. What happens if we put 0.3? What will happen? Ooh, yes, like this. You know what? Let's do something like this, because you only care about the middle. Let's hide F9, or here, hide body F9, okay? I will create a coordinate system here. Because what I would like to do is show all bodies, and I will refine the sizing of these 2 parts, cursor mode body. I will refine it to be 0.25, while 0.25 using the sphere of influence, and the sphere center will be coordinate system, this one, yes? And you'll understand in a few seconds. 5 millimeter radius, yes? This is what we're interested in. This is the most important area, most important region. We can have a quartz mesh elsewhere, all right? 3, 2.5. In order to see something, let's make the piece 0.5, and now we will see the refinement better. Here, you see the refinement? Okay. Yes. I want to do this refinement because I don't want the nodes from the workpiece to interfere, to snap back into the punch. Let's also do something similar here. I will define a coordinate system here. Cursor mode change to face. All right, and here these are not needed anymore because I will I'm refining them with sphere of influence. Size, let's refine the sizing. Control B with sphere of influence, the second coordinate system, sphere radius again, I don't know, 3, 2, 2, okay. And 0.3, why not? Yes. If this blank will try dive deeper into the dial, it will be stopped by these finer elements. Yes. Yeah, let's do it like this. As a displacement, we will assign a fourth step. In which we will retire towards, I don't know, maybe 5. We're back to 7. Yeah, so it will come down, then go back up. Then we should see a plastic deformation in this workpiece. All right, what I would like to do to have a faster solving. Here, let's make 0.7. We don't care so much because the principal contact is here. The point of impact, let's say, is here. We don't care about other faces. Let's see how fast it is going. If it's not going fast, I will cut the mesh. I don't like this too much. This let's make it again. Why not? Let's resize it again. Yes, it looks nice. Let's see how fast it works. Do we have any questions? I think we have. I try to perform, Doctor. It is a simple structure like a ruler. Imagine it has 3 layers: steel, rubber, steel. Rubber with modal. Rubber with modal. It's yeah, it's hyperelastic. I set a bonding connection. I want to see the mode shapes followed by harmonics, but so far it fails. You know what? If you're willing to buy me some coffees, write me an email, and yeah, let me take a look at this, because at least in model, I think I can make it work. Going there in harmonic response, it needs to be seen. But what you say, bonded 3 layers, it should work. So if you're willing to cooperate, yeah, mail me. My plan is to use MSUP for harmonic analysis and transient structure. Oh my god, afterwards, is my approach wrong? What is the right approach? It's a good question. Let's remind everyone what MSUP means. Mode superposition method. Can use instruction for solving dynamic response. We're going in a domain that I'm not very sure. I'm not a master in this domain. But yeah, in principle, I think I can make the modal and harmonic response work. Harmonic response, you give a sinusoidal load, and it should work. It should work. I don't see why. It looks correct. It needs a dive in. Mail me if you want. So where are we here? Does it work? I think it doesn't work. No. Let's stop. How long are we in the stream? 2 hours and something. Come on, dudes, come on. You don't want to, huh? Patience, patience, lots of patience. We need lots of patience. Yes. Yes, we're over here. Okay, nice. I'm keeping this here in order to see the convergence. Geomechanics model in ANSYS. Yeah, but it's not explained. Yeah, nice. I have done something similar. Number 7. CAD-FAM, yeah, I remember about CAD-FAM. I remember they are the top partner of ANSYS. I think they are part of ANSYS now, I think. Oh my god, multilinear kinematic hardening. Yeah, this is solid. Yeah, the spring back effect, yes. Here is the plastic deformation, very nice. They are professionals, yes. What do they have? 8 years ago, come on. Originally, I think they are from Germany. This is why we have some German here. Simulation und Nachhaltigkeit bei Palfinger. Palfinger trifft Robert Schweitel. Trifft it meets. Palfinger meets Robert Schweitel. Simulation is Umsetzung und Ausblick. Ausblick, I think it's overview, and this is setup and overview, I think. Erfolgsfaktor Materialauswahl, Nachhaltigkeit und Innovation bei Schunk. Was ist Nachhaltigkeit? Haltigkeit. Sustainability and Innovation. Oh my God. Simulationsdaten und Prozesse integrieren und managen. Materialdaten für das Engineering, KI in der Produktentwicklung, Product Development. Okay. Yeah, but where are the results? Where is the example? It's only small podcasts or talk show? Guys, it's not appealing. It's not appealing. Let's see. You need to work on the thumbnails. As I said, this is usually done by different people, usually from different departments. Leider selbstverständlich vorhanden. Natürlich mich natürlich machen. Diese Experiment, dieses Versuch in meinem Programm. Ich habe der etwas ganz das zweite ist für mich auch noch relativ motivierend. Wir arbeiten hier mit Strukturen. Wir haben Ergebnisse mit Simulation und Versuch. Und wir können eigentlich immer sagen, Katfim, yeah, the best guys in ANSYS. Stromus this is a CFD stream. This is stream. Stromungsmechanik. Haben Sie auch schon einmal auf Basis einer CFD-Lösung? Please show something. Lots of guys. Please also insert a woman. Who, finally? Displacement Betosi. It's Prozesse und Produkte funktional und cyberischer auslegen. You need to show more pictures, something friendly in the thumbnails. Or, yeah, who am I to tell you this? You know the best. Sorry if I offended you, cat fan. The best of the best. Drei Methoden zur NWH-Berechnungen eines Motors. Alright. Simulațiunea unor small processes mit Rockingen. Where are we? 1.2. It's nice. Tutorials, finally. Years ago. Static Berechnung von Spannung. Let's go for English. Yeah, this is very basic. Something advanced, more advanced. Next time. Yeah, but application and hands-on, zero. Zero application. I mean, no hands-on. No hands-on application, no practice. Theory must be good, but there is no application, and we need results, and we need them now. This is very nice. How does he define the springs? With he also puts a damping? I wanted to simulate something similar a while ago. Yeah, I would like to do something similar. It's very cute, very nice. Only due to gravity? Let's look at the contact a little. Augmented Lagrange. Limbo radius, yes. I want to look at the boundary conditions. Ooh, he is very generous with the substeps. Do we have an initial condition? I want to see if we have an initial condition. Talking about velocity, prescribed velocity. No, yeah, it's very nice. 1.3. Oh my God, this takes so much time. Should we cut it? Should we cut it? Should we cut? Yes. Let's cut it. I will increase the radius of the punch just a little. All right, for faster solving, let's cut it in half. Any question? No more questions. Overview microstructures and crystal plasticity. This is theory. This is important. True versus engineering stress and strain. I'll take a look at the smartphone. It's nice. No notifications. I said that I will increase the radius just a little. 0.4. And I said I'll cut it. Select opposite faces. Let's make a sketch. And the sketch is this thing. There are multiple ways. The easiest way is to just pull. Yes. Should I cut more? Should I cut more or not? You know what? Let's cut more. We need faster solving. Here we're changing to chamfer. Something like this. Oh, something like this. And here, can we? Let's see if I can copy this. Control C, Control V. Can I move it? Oh, yes. 1.5. This is the punch. Now, can I split this body with this surface? Yes. We, I don't know. Does it work? No, it didn't work. Can I combine? Select a target, and this is the cutter. Yes. It's a little desperate, but yes, we have all the excuses because we have we want fast results, and we have all the excuses. Let's also make this a little thinner, just a little. Minus 0.1. This means I will move this with 0.1. 0.1 from the keyboard. Or more. Or more. 0.50. .145. Yes. So this radius is 0.4. This thickness is 0.2. So we should have here radius 0.6. Perfect. We're covered. 0.7 is covered. Let's make it 0.56, 65 just for fun. 0, undo, 0.65. Okay, it's a little bigger than 0.6. We are where we want to be. We need to be creative. Let's make it even thinner. Minus 0.1. Minus 1. Come on. One. Perfect. Save. Let's remake the contacts. All right, so this is the punch, which should be made of steel. Should we make it rigid? Not at this moment. Should we or not? Let's see how it works. Select a face. This is the face. Coordinate system connections. Frictional die to piece. Show die to piece. Okay. Piece to punch. This means we need to. It looks correct. What is the problem? It lost something? Whatever. Delete. We have this. And we have this. All right. Mesh. Punch. On punch, it was only this small face. All right. Let's see. Element size. This one, this one, this one. This one. This should include also the punch. Now we can make the radius even smaller. Yes. All right. Rename based on definition on die. What do we have here? This one. Can we make it smaller? Yes. On punch. Yes. Save. Ooh. All right. So 0.2. We need to decrease all the values. 1, 0.4, 0.2, 0.2, 0.15. Let's see where we need to refine. Okay, let's make it this 0.15. This is one. Let's make also the punch to be one. All right. I also want this one to be made of tetrahedrons. Yes. What about the faces? The faces, these faces. These faces. All right, yes, because we do not care too much about them. Sure. This radius I don't like too much. .15, yes. Yes, now it looks nice. How 22,000. Let's leave the entire piece. Let's leave it 0.15, and I will delete. I will exclude. All right. And now we will have two elements per thickness. Do we need these or not? Do we need or not? No, we don't need it. Not in this model 0.2. Yes, but I want again to include it here. Here I want to include it. Yes, 0.15. There is a trick, this trick. We can offset along the x-axis. With how much? 0.2? Because I'm interested mostly in refining the blank, not the punch. Yes. Even more here, 0.3. And I will 15,000. Yes, nice. You know what? Let's leave it like this. We have half the mesh that we had before, which is perfect according to my desire. What do we push? This, this, this. We push everything. This and this. Let's push it downwards. All right. Yes, again. Frictionless support. Also this face, because you lost a face due to the cutting operation. Displacement. We have a displacement. Fixed support. Let's extend it. Here and here. Perfect. Save. Solve. It should solve much faster. Come on, come on. Much faster. Yes. Ooh. There is a problem with the contact. Let's see. This contact. You remember I told you before about the spring back effect of this lamella and about it going here, but I don't know if the problem is here. Maybe the problem is here. Maybe. Huh? Yeah, this sizing is too coarse. Let's extend the sizing a little. The refinement. Let's extend the refinement. Yes, and will we reach there or not? Here also, let's extend here. I don't like this mesh. I don't like this mesh. Let's see if it works. Come on. Yes. Perfect. Remember also when things don't go according to plans, to check time increment. It lowered until 6e minus 3. Then if it goes up, we're fine. If it goes down and like here, then yeah, it's not so nice. This means yes, this is what it means. You see, because we don't have a fine mesh here, it's very coarse. These nodes are not meeting enough nodes. So the nodes from this part, they pass through here, yes? We can say this is a soft region, this is a stiff region. This means we need to clearly refine as we did here, yes? We need to refine here, but not only on the surface. We need to refine in depth in this region. So take into account a refinement on the surface, it's not very useful and it's almost useless. Almost at all times, it's not useful. So let's create coordinate system here. Also a coordinate system here. All right, and now we're going to duplicate this one and choose here coordinate system 3. I would like to move a little the coordinate system according to along z and x to be more here in the center. closer to this edge because now it's located in the center. So let's go offset x, I don't know, 0.5, with minus, of course. And offset z, yes, minus 0.5. Yes. Look here, yes, it goes where we want it. Sphere radius, why 1? Why not 0.5? Why 0.7? Why not? Let's move it a little up. 0.3. Yes, I like it. Duplicate. I will select here coordinate system 4 and do the same with the offset. Do offset around z minus 0.5. Minus 0.5, and the offset around about x is minus 0.3. One should be with plus this one. I forgot about the minus. What am I doing wrong here? I should have plus. Yes. Yes. So we have a mesh refinement here. And we will avoid this stiff area to penetrate here. We'll avoid this, hopefully. Save. Solve. Do we have any questions? Clear generated data. Clear generated data. Solve. It works. No. Clear generated data. Solve. Clear generated data. Solve. We need patience, of course. So it started. All right. Do we have any question? Hello. Can you remind us the purpose of this essay? What is the end results? Should we have to see? It's not more like an end result, but it's also the process. Okay. In this live stream, you see how an FEA engineer works. How is he thinking? What refinements should be made? For example, when there are errors, where should we refine? We refine the mesh. We gradually apply the load. And yes, in the end, look at the name of the stream. The name of the stream is plastic deformation. And this is what we're doing. We're analyzing something with plastic deformation. What the struggles that I'm doing now, you will not see them on YouTube. because nobody will stay for hours and do this. They will present usually the final results. So you have the opportunity to see how if a engineer, specialist, expert thinks, and how when he gets stuck, namely me, yes, what solutions is he thinking about? What am I thinking about? How to overcome, how to avoid problems, how to solve, yes? This is the purpose. Should you refine also here? Why not? Yeah, let's do it. Should we refine it more or not? When you see a live session, you see the struggles and the train of thoughts, my train of thoughts, okay? Which comes from so many years of FEA. So these trains of thoughts, the planning, the overcoming obstacles, they are not taught. They are not in any. They do not exist. They are not described in any book, in any planning or training. So, yeah, yeah. Some people may find use in these streams. And also we need patience. Lots of patience. I think I exaggerated a little with the oversimplification. I think. And now I suffer the consequences of wanting to solve the FEA very, very quick or much faster. Yeah, it works nice. It works nicely. Thank you. Thank you too. True. The quality is so nice. Oh my God. This is a properly defined stress-strain curve. So he used, I think, multilinear kinematic hardening. Here is multilinear isotropic hardening, and here is bilinear isotropic hardening. And here is elastic only. I understand. We have second one. Let's go for second two. Yes. Where are we here? Yeah, multilinear isotropic hardening, yes. What? It's a cute name. Fairy tales. Cute name. What ANSYS version is this? It's a recent ANSYS version, 2024 or 2025. 2024, yes, or two. This should be checked out because it's important. So there are. Oh my God, this is a nice mesh. He's looking at the values for the quality criteria. Yeah, this is professional mesh. He tried with linear adaptive region. Yeah, not so easy. Look here, yeah, the curve. Elastic and plastic. This is the necking, and I would like to see some stress. There's look here, if plasticity is not defined, yes, 7,000 megapascals, which is nothing. It's not useful at all. But afterwards, he will go and show for the other specimens, I hope. He filtered with 250, which is the yield limit we say for this material. It's a standard structure still. It would have been cuter if he, at least this, if he would have quit showing these results and only showing the other results. To have a scale with a few hundreds, not dozens of thousands. It's yeah, it's very nice. He explains in details, yeah, and it's very useful. I would like to check his channel videos. He goes in detail. And this guy is a professional. Yeah, I will subscribe to this. He knows what he's doing. Mr. Anton Vasiliev, thank you, plastic computation. For 10 days. Saprobasny, Ukraine. This about qualifications. Does it exist anymore? Oh, yes. Oh. And the cat. I should also provide the cat for the live stream. Oh, this is nice. Saprobasny. Let's see the website. Різниця між сьогодні поговоримо про ще протиже та генеративізація, а також про чи завжди потрібна оця оптимізація, хоч у вигляді генеративного дизайну. Maybe this is хочу, хочу. Вигляді чогось простішого. Також визначимо, це таке генеративний дизайн в теорії та в розумінні Autodesk, і чому і певні do have a translation. It's like a blog, and this is about that. So the main of this person. Be careful with this since it does not that is completely. He's from Kharkiv Polytechnic. My phone number. Yeah, this guy is doing. Yeah, real expert. We need to respect the experts. Where are we? 1.4. Yes. Why not? So I found something nice today. Topic similar, ANSYS. What is this? Normally, if purchase your simulations, what will you provide? Can you show us example? It's written there. It's written there. So you have the ANSYS file and the 3D model. This is all. You open the ANSYS file and you see the material, the boundary condition, everything. This is what you get. Or you also have tutorials and you have step-by-step the instructions. Yes. Let's go. What is plasticity, linear, non-linear? What? So he what? I think he's forming. He's plastically deforming. But do we have stress or strain? Oh, what? Come on, dude, what are you doing here? Plasticity, what do you mean plasticity? Without, you don't define hardening? Dude, you don't define hardening? Why? Why don't you define hardening? The mesh is kind of coarse. Yeah, but you see, because you don't have plasticity, it goes back, so it's elastic deformation. So do you have plasticity or not? Let's see here. Let's hope he has. Polyethylene. What is this? Plastic deformation means deformation of plastic. What? Multilinear isotropic harmonic. Fine, yes. So show us. Yes, this is plastic deformation, yes. Animate. Yes. Finally. 29,000 subscribers, yes. ANSYS complete course. He had the course and he put it online on YouTube. Project. Oh, I know Hindi. Project. Planning. Now it's easy to see. Project planning. Usni se banaye. Usni se banaye. This is what the ANSYS lady did, I think, with the paperclip. I think. Kose banaye. What does it mean, kose banaye? Kause banaye. And here is banate. Come on. Banaye or banate? Dude, please be consistent. Let's see if we can find out what he's saying. Banaye, yes. Make. And banate, I think it's not correct, no? Banate. Making. Yes, banaye and banate. Oh. So he's, of course, it's his language. He knows. I think he explained this, so he explains it very well. Yeah, I think he does a very good job. Yeah. Did I subscribe to him or not? Subscribe, okay. Yeah, he's doing a nice job. What do you mean crash? Crash on what? If you say that it's crash on water, then you have my respect. 1.6, all right. On floor, on soil, yeah. The mesh is cute, I like the mesh. If this is millijoules, this means that the model is very small. Yeah, 100 millimeter. If the model was real size, we should have had kilojoules, megajoules. This is a toy, let's say. But yes, nice. Types of energy, inertia, kinetic, total. Yeah, nice. Nice work. Kause, I think it's case. Kause, okay. Dosto or docto? Dosto. Drigano. Metri. How Bahut. Usna or Usan. How Uskarać. Uskarać, okay. This is hypermesh. Kause. Bane. Okay. Yeah, pretty cute. Normally, if you purchase, okay, we answered that. Where are we? Here. So, how long is the stream? Maybe we should close it. 3, okay. Can we make it faster? Let me think if I can make it faster solving. To solve faster. Let me interrupt a little and show you Plasticity stream. Then I will try and make it faster. If it does not make faster, we'll end the stream because yeah, it takes too much time. We predict and we will see that it works. The solving does not stop. Let's force it to stop. Clear generated data, evaluate our results. So it goes pretty nice. Do we have a plastic strain? Yes, we have plastic strain. Let's duplicate and make the punch and the die rigid to see if the solving is faster. look at the smartphone for a few seconds. Okay, it's nice. Things will be much easier when we go to explicit dynamics. We will not have convergence problems there. Let's see if I can make the die and the punch rigid. This means we need to right-click, flip contact and target. Right-click, flip contact and target. Now, we cannot use these. Instead, we need to create some joints. One of the joints is fixed joint. This will be fixed. And the other joint is translational joint. We're going come on. I didn't hit okay. Now we're going to have a joint load, translational joint load. Let's orient the x-axis. The x-axis, let's make it collinear to the global x-axis. Yes, so x-axis, make it collinear to the global x-axis. All right. Because we have translation defined on the x-axis. This means on the joint load, we're going to choose displacement, and magnitude will be tabular, and we will copy these values. So now we're working with rigid bodies. All right. Out of curiosity, can I make this sizing? Can I make it 0.2? Maybe not, but we will see. I have 10,000 nodes, and I would like to have a very fast solving, if possible. So remember, the parts that are not important, you can make them rigid. We only investigate the workpiece here. Does it work? Of course not, because we have this problem with the rigidity here. Let's go back to 0.15, generate mesh, and maybe we'll refine the, let's refine these two. Or no, let's leave like this at this moment and solve. Yeah, hit something. But it works. Introduction to FEA. Busting pressure, analysis of water bottle. Yeah, this is something very cute that I have done a while ago. Due to the plastic deformation, heat is generated. You can see some energy. You can ask yourself why is 2000? Claudio said not to have thousands. I think it's not defined with bilinear isotropic or multilinear isotropic hardening. I think it's something default from the explicit dynamics library. This is why we can have such big values. This plus deformation is very nice. It looks very nice. I'm interested in having the temperature, yes. So we have above 110 degrees. It's like forging, but the workpiece, the sword is not previously heated, so it's cold forming, it's not heat forming. It's not real forging. Sword forging, I would say. I don't think it's real forging. Let's see how do they define forging. If it's necessary due to heat. Yeah, it's not necessary due to heat because the bristle method by hammering. Yes, so it's correct. Sword forging, it's correct. Yes, come on. So this is like a... This is the punch, and this is the die, let's say, from two pieces, two parts, yes? And yeah, it reminds me of my one of my first simulations published, respectively forming, dying, deep drawing, forming. This is very simple and cute. that easy. So let me, maybe deep drawing. Yeah, this is, oh my God, I worked so much for this. It was made, how much? 13 years ago. So much work was this, oh my God. So you can see, yes, we used Bilinear isotropic and it's plastically deformed. It's very nice. We were asked to change the website name to explicit to not include ANSYS, and yes, I did it. Now it's explicit.com. Very nice. This is cute. Yeah, this is flaccid deformation. In static structure, yeah, not explicit dynamics. Very nice. What second do we have here? 1 point. It's like a deep drawing. For colleagues watching, hello, thank you for watching. All right, and here we have blanking or cutting. This is another example of plasticity, vibro burnishing or vibro rolling with a ball. Yeah, it hardens the surface of the material. Very nice. Very much work. Very nice. I want to see if it's made in static or explicit. I think it's made in static. Yeah, it's not mentioned. In one of the next webinars or streams, we'll do something from the fracture mechanics side. Yeah, very nice. very nice. This is cute. Let's also look for other people's if yeah, not many people go in plasticity and plastic deformation. I think you wanted to say linear elastic, I think, not linear plastic. Yes. Yeah, linear elastic, not plastic. Abacus. This is something simple that I made with plastic deformation. Basket hoop, which is deformed plastically. Basketball rim. This is an example of plastic deformation. Yeah, it goes faster as I hoped and predicted. Very nice. What is this? Equal channel angular pressing and nonlinear adaptive region in ANSYS. Oh. This is plastic deformation. I would like to see the nonlinear adaptive, and yeah, we see it here. What is the initial shape? He has a radius here. If okay. If he had a live edge here, then it would have been some problems, I think. But he has a radius. Yeah, very nice. He has more FEA. Yeah, we're approaching something. I like the stress values. We're definitely on the right path. He's analyzing this part. This. Kamchatsky. Petropavlovsk-Kamchatsky. Okay. Such a nice model. Such a nice model. I like the mesh. I like the mesh. Very fine mesh. And these are the welds. The weld scenes. Do we have animation? Heat. Heat during welding. Okay. How did he simulate the weld? Welding induced resistances, but how? Pen and paper. Do you have a Korean of export engineering? Can export a B-rep? I've seen measured. I consider it wrong, but the modeling is. Yes. Mr. Kev, nice job. So, a beam fixed with the force. Why? Why? This is cute. Oh, I should do something like this. This is cute. Oh my god. Plastische Verformung, whole round double. This is cute. Yeah, this is something that I like. Uh, 100% explicit dynamics, I think. Gesamtverformung eines whole round doubles. Yeah, explicit dynamics. Augment Lagrange pure penalty. This means it is not explicit dynamics. If this is not explicit dynamics, then it was a lot of work. So much amount of work. Ah, yes, it's not explicit dynamics. Because he didn't define the self-contact. Here there are self-contacts between this face and this face. There are self-contacts. And here we see that the mesh is colliding. It would have been almost a perfect FEA, but he forgot to, or he doesn't know to apply the self-contact. So he has a contact between the screw and this nut, contact between the head of the screw and this whatever plate, what is this? And he forgot to define this contact. It would have been a perfect simulation, but it's not perfect. It's very nice, but not perfect. This movement is due to other contacts here, but not due to the self-contacting here. It's an overlooking. It's not something very serious, but it's not 100% perfect, let's say. But yeah, it's very nice. Ooh, the FA stopped. And I think we'll leave it here. So it goes, then it retires, yes? And here on the travel, on the back travel, I should have discretized. So going from 11 to 10 to 9 to 8. And yes, we have a deformation, we have a spring back here. Yeah, so we have contact here, and this side of the lamella touches this sponge. We have a spring back. There is plastic strain, plastic deformation. Yeah, so if you want to see more, check my website for similar FEA. And you can always search expect FEA, plasticity, or deep drawing, stamping, forming, and you will find anything that you need. Very, very, very nice simulations. Thank you very much for your attention. I will leave you with these results. Yeah, see you in the next live stream. Thank you very much for your attention. Bye-bye.